We present CC-3DT, Panoramic 3D Object Tracking via Cross-Camera Fusion. To track the 3D locations and trajectories of the other traffic participants at any given time, modern autonomous vehicles are equipped with multiple cameras that cover the vehicle's full surroundings. However, current camera-based 3D object tracking methods prioritize optimizing the single camera setup and resort to post-hoc fusion in a multi-camera setup. Thus, they fail to track objects moving across cameras, which limits motion modeling to short single-camera trajectories both during training and inference. We propose a method for panoramic 3D object tracking that associates and models object trajectories both temporally and across views, improving the overall tracking consistency. Our method fuses 3D detections from multiple cameras before association, reducing identity switches significantly. We obtain longer and cross-camera object trajectories which significantly improve motion modeling, leading to further improved association and smoother trajectories across camera views. Here is the overview of our method. First, the 3D estimation stage extracts the 3D object detections for each camera independently. We can use any 3D detector to obtain the location, dimension and orientation of each object. Additionally, we utilize an appearance feature extractor to get appearance features for the association stage. Then, we lift all detections from the camera coordinate system to world space and merge them with non-maximum suppression in 3D, obtaining a single set of multi-camera detections. Next, we associate the detections with existing tracks by combining appearance, 3D location and velocity cues. We use an LSTM-based motion model to predict the location of existing tracks in the current time step. Finally, we use our motion model to refine the predicted object location, dimension and orientation based on the long-term cross-camera trajectory history, leading to smooth and precise object trajectories. We compare our method with a single camera baseline, CC-3DT, and a naive merging of single camera results. While the naive merging helps to alleviate the ID switches between cameras and improves the AMOTA, we observe a larger gain in AMOTA with our method. The ID switches are cut in half compared to naive merging, highlighting the effectiveness of cross-camera association. Further, our ablation study shows that motion modeling improves by leveraging cross-camera trajectories. We observe a higher gain in AMOTA when using a motion model versus using none compared to naive merging. The visualization of the results shows that our CC-3DT provides a smooth and precise trajectory across cameras, while the baselines struggle with a car moving across cameras. We further show that long-term cross-camera trajectories also help the motion model training. They provide larger amount of training trajectories at greater diversity as longer, more complex trajectories can be modeled. On the NuScenes benchmark, for the both testing and validation set, we outperform the previous state-of-the-art method, MUTR-3D, even with a weaker detector. Since our method is agnostic of the 3D detector, we can utilize stronger, recently published methods and surpass the state-of-the-art by a large margin. Also note that our AMOTP is significantly lower, meaning that our trajectories are more precise. We also have the lowest ID switches, meaning that our association works best. We test our hypothesis on another large-scale driving dataset, Waymo Open, and the results corroborate our findings. Our method performs better in MOTA than the single-camera CC-3DT, while also having a lower mismatch ratio, meaning that we have both better overall and association performance. Our qualitative results on NuScenes dataset. Our qualitative results on Waymo dataset. Thank you.